Hey everybody. So we're getting into our next and final unit of the year, all about trigonometry, and we're going to be really looking at graphs of trigonometric functions and applications. But before we do that, I want to take a step back and review a little bit from geometry and look at some right triangle trigonometry, just to kind of get these ideas planted back in our head here about what this is. So this video and the next few videos are just all related to that review. So let's recap first. We've got three functions. We've got sine, we've got cosine, and we've got tangent. So sine, oops, that's supposed to be a different color. Cosine and tangent. And no, I don't want to hear you call anything sin or cos or tan. They are function names. Don't do that to me. So you're going to see this symbol here a lot, angle theta. Theta is a Greek symbol, and it's just a variable. We'll just as often see x or other variable names, but theta is a very common angle name. So if we have an angle theta in a right triangle, right, there are three sides that we could be dealing with. We could be dealing with the opposite side, which is the side across from it. We could be dealing with the adjacent side, which is right next to our angle theta, or we could be dealing with the hypotenuse, which is always, across from the 90-degree angle. So we're reminding ourselves of those terms, the hypotenuse, the opposite, and the adjacent side, and just how they relate to an angle. It's never going to be this side's always opposite, this side's always adjacent. It's relative to an angle. So if I want to find the sine of that angle theta, I'm going to take the value or the length of the opposite side and divide it by the length of the hypotenuse. If I want to find the cosine of that angle theta, I'm going to take the length of the adjacent side and divide it by the length of the hypotenuse. And if I want to find the tangent of that angle theta, I'm going to take the length of the opposite side and divide it by the length of the adjacent side. And so back in geometry, you probably got this nice little reminder, SOHCAHTOA. And remember that the S, the C, and the T relate to sine, cosine, and tangent. And then the following letters tell us which sides to divide by what. So opposite divided by hypotenuse, adjacent divided by hypotenuse, or opposite divided by adjacent. So as we go through this review, there are going to be some times where I ask you to do some sample questions on your own and answer here. Then there's also a couple of practice questions along the way. So as always, please feel free to take a break or do anything that you need to do. So I just want to practice using these trig ratios here. I've got this triangle ABC. We've got two legs. Remember, legs are the sides that attach to the right angle. And then the hypotenuse is blank, but the hypotenuse is actually 17 units, which you could verify using the Pythagorean theorem. I'm not going to do that right now. You can verify that on your own. So the first thing that we're doing is we're finding the sine, the cosine, and tangent of angle A. So angle A is right over here, which means we're relating these few values to angle A. So sine of A is the opposite over the hypotenuse. The opposite of A is 8, and the hypotenuse is 17. So we'll say 8 divided by 17, and we'll leave it like that. We do not need to turn it into a decimal. The cosine of A is the adjacent angle divided by the hypotenuse. So I'm going to take 15 and divide it by 17, and I'm done. And then finally, tangent of A is the opposite divided by the adjacent, and this is just where people make a silly mistake is they just put the fraction upside down. So the opposite is 8, the adjacent is 15, so this will be 8/15. So we can do the same thing for angle B, right? Angle B is over in the top right. angle B. So we're again going to find the sine, the cosine, and the tangent of angle B, starting with the sine of B. So we need to locate the opposite side. The side that is opposite from B is 15. So our sine of B will be 15/17. The length of the hypotenuse doesn't change. The hypotenuse is always the hypotenuse. The cosine of B is the adjacent side divided by the hypotenuse. So the length of 8 divided by the length of 17. And then our tangent of B is the opposite divided by the adjacent. So our opposite length was 15 and our adjacent length was 8. Notice we're never going to find the sine, cosine, or tangent of angle C here because C is that 90-degree angle. It's the special angle there, and there's no the adjacent and the hypotenuse and opposite relationships just don't exist for it. So again, these next two examples, I'm going to ask you to try. Example A will ask you to find the values, the sine, the cosine, and tangent of L, and then have you check your answers here and walk through them with me. Example B will have you try those, and I will show the answers here, and you can always follow up with me if you have further questions. Sine of L, the opposite of L is 6 divided by the hypotenuse of 10, and you might have simplified that to 3/5. Cosine of L, well, adjacent to L is a length of 8. The hypotenuse is 10, so that is simplified to 4/5. The tangent of L is the opposite over the adjacent, which is 6 divided by 8, or 3/4. So a much more useful application of trigonometry here, especially when it comes to right angles, is to find the lengths of missing sides. We can also use this to find missing angles in triangles, but we're not going to do that today. We're just going to focus on missing side lengths. So the key steps to finding the missing sides of the following triangles is really to answer the question, which relationship are we dealing with? Right? Which one, sine, cosine, or tangent? And I'm just going to rewrite my little SOHCAHTOA reminder here so that I can use it as needed. So in example 1, we're given that the hypotenuse is 7, right? It's across from the 90-degree angle. And we're given an angle that is 70 degrees, and we're looking for a missing side of x. So I'm going to be looking for, what are the relationships between these values? Well, x is opposite of the 70 degrees. And so since I'm dealing with an opposite and a hypotenuse, that tells me I'm going to be using sine. This says that sine of 70 degrees is the opposite over the hypotenuse, x over 7. Now, when you're calculating the sine of 70 degrees or any trigonometric value, we want to make sure that our calculator is in degrees mode. So if you're using a handheld calculator, you're going to want to select the button that says mode. If you're using a digital calculator on your computer, I recommend Desmos Scientific, not Desmos Graphic. Oops, that doesn't say scientific. Desmos graphing uses a different unit called a radian that we're going to talk about in maybe next week or the week after. So do not use Desmos graphing for right now, just use Desmos Scientific or a handheld calculator that is in degree mode. Okay, so we can find the value of sine of 70 degrees, or we can isolate x, because that's what we need to do. We need to solve for x. To get x by itself on the right-hand side, I want to undo that division by 7 by multiplying both sides by 7. And when I do that, I get x all by itself, and I get that x is equal to 7 times the sine of 70 degrees. And so I could put that in my calculator again, one of these two options here, and I will get approximately 6.578. I think I'm going to round to 3 decimal places here as I do these questions. So again, the trick is identifying what relationship, sine, cosine, or tangent are we dealing with here. So let's look at example 2. Example 2, we've got an angle of 65 degrees, and we're given that the opposite side is 10 and the hypotenuse is x. So again, if we're dealing with an opposite and a hypotenuse, we should relate this to sine. So the sine of 65 degrees is equal to the opposite 10 divided by the hypotenuse x. So if you just look at the setup here, this one's a little bit different than example 1 because now our x is in our denominator. So this one will take an extra step to get x in a position that is actually helpful for us. So the first step we need to do is we want to get x out of the denominator. We're going to multiply both sides by x, right, and reduce that right-hand side. So we get x times sine of 65 degrees is equal to 10. And now I haven't isolated x. I really need to do that. So I can actually divide both sides by sine of 65 degrees because really that's just a number. We haven't calculated it yet, but that doesn't change the fact that it's just a number. So when I do that, I will get x is equal to, I'm just going to rewrite that 10 divided by the sine of 65 degrees. And when I put that into my calculator, I get approximately 11.034. So being really precise here, just because we really want x in the numerator doesn't mean that that's always how it's going to be set up. So pay close attention to those relationships, and I find it really helpful to actually label, as I've done here, which side is the opposite, which side is the hypotenuse. Okay, we've got 2 more examples together, and then you are practicing on your own. You're doing a great job. So example 3, I've got the angle 24 degrees, and opposite of that, I have 4, and the hypotenuse is x. So this setup is going to look pretty similar to that last one. Sine of 24 degrees is equal to the opposite over the hypotenuse, so 4 divided by x. With similar algebraic manipulation as in example 2, I would get this to be x is equal to 4 divided by the sine of 24. And remember, when you're using your calculator, it's got to be in degree mode or it's got to be Desmos Scientific. And I will get x is equal to 384. How about 834 when we round to 3 decimal places? Okay, one more example. I promise this one's just a little bit different, so let's check it out. So in example 4, we've got an angle of 55 degrees, and we've got the side opposite the right angle, that is the hypotenuse. And this time we've got an adjacent side length, right? The leg that's right next to the 55 degrees is x. So since we're dealing with adjacent and hypotenuse, that's going to be our cosine. So the cosine of 55 degrees is equal to the adjacent side divided by the hypotenuse. So cosine of 55 degrees is equal to x divided by 20. I want to isolate x, so I'm going to multiply both sides by 20. And so I'll get 20 times the cosine of 55 is equal to x. And when I use my calculator there to simplify that, again, make sure we're using degrees, I'm going to get x is approximately 11.472. So it's definitely a little bit harder to find missing lengths than it is to just simply identify the relationship or identify the trigonometric ratio as in those earlier examples. But again, it comes down to this question: which relationship are we dealing with? So as you check out these practice problems, make it very clear. Use the picture to your advantage and pay close attention to how the triangle is oriented and what information you're given. Examples E and F are just a little bit different, but I encourage you to try them out. Again, they're really similar to the questions that that we just looked at. So do your best. Check in with me if you have any questions, and I look forward to talking to you on Zoom.